Hello everyone, this is Yashveen from Exam Help Web. In this video, we'll be solving paper 2 variant 3 May June 2024 AS level physics. Starting with question 1, where the drag force acting on a sphere falling through a surface is given by 6 pi multiplied by the viscosity. Okay, let me change colors here. Right, viscosity and the radius of sphere multiplied by the speed of the sphere. So you have a sphere falling through a liquid, and we know that whenever an object falls through a fluid, it will experience a force of upthrust. So just keep it in mind. We'll probably need that going further into the question. Part A show that SI base units of viscosity are kg per meter per second. So SI base units include kilograms or meter, seconds, ampere, and Kelvin. Now, to find the SI base units of viscosity, you will first need to make it the subject of formula. And following the formula given in the question, viscosity would be equal to drag force divided by 6 pi radius and speed. Now, force in terms of SI base units, the units are kg meters per second squared divided by the units of the denominators. Now 6 pi is a constant, so there's no unit for that, and radius is a length which is measured in meters multiplied by the unit of velocity, which is meter per second. So here you will cancel out the common units that will leave us with kg per second, and then the meter would shift from the denominator to the numerator. So that's kg per meter per second. The sphere has a radius of 3 centimeter. You probably need to convert this into meter for calculation purpose. And it's falling vertically downwards at a terminal velocity of 2 meters per second. So terminal velocity means the velocity of the sphere is going to be constant, and the drag force acting on the sphere is 0.096 Newton. Calculate the viscosity of the liquids, just a 2-mark answer. And as we said earlier, viscosity is equal to drag force divided by 6 pi radius and velocity, which is 0.096 divided by 6 pi multiplied by radius, which is 0.03 multiplied by 2, and that leads you to 0.085 kg per meter per second. The sphere is shown in figure 1.1. Okay, so it's going to fall down with or move down with constant terminal velocity. On figure 1.1, draw and label arrows to represent the direction of 3 forces acting on the sphere as it falls at terminal velocity through the liquid. Okay, so because it's falling through the fluid, it is going to have an upthrust force acting upwards. That's a well-known fact. And then we just saw the drag force. We just saw there's a drag force acting on the sphere. Drag force also acts opposite to the direction of motion, so that will be upwards. And because this sphere has mass, it's going to have weight as well, which will act downwards. D part 1, the density of the liquid is 90 kg per meter cube. Show that the upthrust acting on the sphere is 1 Newton. Now, according to the syllabus, you are required to know the formula of upthrust, which is equal to density multiplied by gravity multiplied by volume of the object, which is falling through a fluid. In this case, we are supposed to find the upthrust. The density here is 920 multiplied by 9.81 multiplied by the volume of the object which is falling. In this case, that's the sphere. So the volume of sphere is 4/3 pi r cube. So that will be 4/3 pi. The radius is 0.03 meter cube. And this will lead you to 1 Newton of upthrust force. Part 2, calculate the mass of the sphere. So you have the to answer this question, you will need to understand the concept of terminal velocity. When an object moves with constant velocity, meaning its acceleration is 0, and according to Newton's second law, resultant force is equal to mass into acceleration, or in other words, the net force is proportional to acceleration. When acceleration is 0, the net force acting on an object must also be 0. And in the case of this sphere, we see that it is moving with constant velocity. That means the sum of all of the forces acting on the sphere must be equal to 0. And in this question, we are going to consider these 3 forces acting in the vertical plane. And what that means is when you add up all of these forces, which is upthrust and drag force and weight, they must be equal to 0. Because upthrust and drag force act in the same direction, that means weight must act in the opposite direction. Now you can take either of the directions as positive or negative. I'll choose to take weight as negative here. So upthrust plus drag force minus weight must be equal to 0, since all of these are forces, which is a vector quantity. And what that means is upthrust plus drag force, the sum of them, must add up to the weight of the sphere. So we know the upthrust is 1 Newton. The drag force was known to be 0.096 Newton, and this must be equal to the weight. So the weight is equal to 1.096 Newton. Weight is equal to mass multiplied by gravitational constant. Therefore, mass is equal to 1.096 divided by 9.81, and that's 0.11 kilograms. Question 2a, define displacement from a point. So displacement, being a vector quantity, will have magnitude and direction. It is the shortest distance measured from a point with its specific direction. B, an object is projected horizontally at a speed of 6 meters per second. When an object is projected horizontally and you are not given any information about its vertical speed, it's safe to assume that the vertical speed here will be 0. From a slope as shown in figure 2.1. Whenever you see a question where you're given information about horizontal and vertical speed, you will need to start recalling all of the information you learn about projectile motion or motion in 2 directions. The slope is at an angle of theta to the horizontal. Air resistance is negligible. The object lands on the slope at a time that's 0.71 seconds later. So this is the time for traveling, and this is the constant horizontal velocity, and stops without rolling or bouncing. Part 1, determine the horizontal distance traveled by the object. Because the horizontal velocity remains constant, and you are also given the time taken for this horizontal distance traveled, that means you can use the formula speed is equal to distance over time to find the distance traveled, which will be 6 times 0.71, and that is equal to 4.3 meters. Part 2, determine the vertical distance traveled by the object. Okay, as I mentioned earlier, you need to have your knowledge for projectile motion to answer this question. And in the vertical dimension, there's always going to be the gravitational force acting on an object in motion, which leads to the acceleration being 9.81 meters per second squared. We know initially the vertical velocity is equal to 0, and the time taken for traveling for both vertical and horizontal distance is always the same in such scenarios, which is 0.71 seconds, and we are supposed to find the distance traveled. In this case, the most suitable formula to be used would be displacement is equal to ut plus half at squared, because the ball will fall under force of gravity. That means it's going to have the acceleration, which means you can use one of the four formulae for motion under constant acceleration to find the distance traveled. So initial speed is 0, which means this product would be 0. Therefore, the distance is equal to half multiplied by 9.81 multiplied by 0.71 squared, and that's equal to 2.5 meters of vertical distance. Use your answer in B part 1 and 2. B part 1 tells us the horizontal distance is 4.3 meters, and part 2 tells us the vertical distance is 2.5 meter. To calculate theta. Okay, so as you can see, this forms a right angle triangle. When you consider the vertical distance and the horizontal distance, and you want to find the angle between the slope and the horizontal distance, this forms a right angle triangle with adjacent and opposite sides to theta already given to you. That means you can use a trigonometric formula where tan theta is equal to opposite side divided by adjacent side. So theta is tan inverse of that, which will be 30 degrees. Part 4 asks you to determine the magnitude of displacement of the object from its original to final position. So the object starts from, let's say it starts here initially, and finally when it has covered a vertical distance of 2.5 meters and a horizontal distance of 4.3 meter, it will reach this point over here, and you're supposed to find this length. Now can you see, this angle is 30 degrees, the base or adjacent side is 4.3 meters, the opposite side is 2.5 meters, and you are supposed to find the longest side in this right angle triangle. And you can do that using the Pythagoras theorem, where the hypotenuse squared is equal to base squared plus height squared. Therefore, the hypotenuse squared, or the hypotenuse, represents the displacement. So the displacement would be equal to square root of 2.5 squared plus 4.3 squared. And that's because you take square root of both sides here, which cancels the square of hypotenuse side. And this leads to 5 meter of displacement. By considering energy, calculate the speed of the object just before it lands. What they really mean here is consider the change in energy of the object between the final and initial positions. Here's the initial position where the object has horizontal velocity, and also it has a distance of 2.5 meters from the ground. And using this knowledge, you need to know just from the height it will have gravitational potential energy, and the fact that it has horizontal velocity means that it also has kinetic energy due to speed at the top. And at the bottom, when it doesn't have height, that means the gravitational potential energy at this point is equal to 0. According to the law of conservation of energy, energy can neither be created nor destroyed, and since we are not talking about energy lost in heat or work done against friction, that means all of the energy at the top must be equal to all of the energy at the bottom. What that means is energy at the top includes kinetic energy plus the gravitational potential energy. It must be equal to the kinetic energy finally at the bottom. And that means all of the gravitational potential energy which was initially stored in the ball will now be initially stored in the object will now be converted to kinetic energy, which is why it will gain speed, or which is why it will have more speed at the bottom. So kinetic energy initially plus the gravitational potential energy lost, is the sum of these two energies will be equal to kinetic energy at the bottom, where kinetic energy is equal to half mv squared and gravitational potential energy is equal to mass into gravity into change in height. So that means half m into v squared, which is 6 at the top, plus mass into 9.81 into the height at the top, which is 2.5, is equal to half into mass into v squared, which is unknown. Now we are not given with the value of mass in the question, and you don't need to know that either, because as you can see, you can just multiply both sides of the equation by 1 over mass, and this will cancel out, or divide both sides of the equation with mass, and so you don't need that anymore. And finally this is equal to v square is equal to square 85.05, therefore speed is square root of that, which leads to the final answer of 9.2 meters per second. Question 3a, state Hooke's law. According to Hooke's law, the extension is proportional to applied force. This is concerned with objects that can be stretched or compressed in terms of formula that is equal to F equal to kx, where k is the spring constant, F is the applied force, and x is the extension. B, the variation of applied force with the extension for a sample of a material is shown in figure 3.1, where force is given in Newton and extension is given in millimeter. Always be careful of units, because we never work with millimeter. You will always need to convert this to meter if you need any of the values for calculation. The sample behaves elastically up to an extension of 80 millimeters. Okay, what does that mean, elastically? Under elastic extension, an object will extend such that when the force is removed from the object, it will return to the original length, whereas when the object exceeds its elastic limit and proceeds into the region of plastic extension or plastic deformation, when you remove the force from the object, it will no longer go back to its original length. It will be deformed. Now they're telling you the sample behaves elastically up to an extension of 80 millimeters. Okay, so this is the point where it behaves in an elastic manner. Let's just make it easier for ourselves and find the y coordinate right now. We'll probably need to use it later of this point. It's halfway between 6 Newton and this point here. Let's find out what the smallest unit of the graph represents in terms of force here. So that's 2 divided by 10, which means the smallest unit is 0.2 newtons, which will make this 5.8 Newton. And halfway between 5.8 and 6 Newton would be 5.9 Newton, which is the point at which extension is 80 millimeter and also the elastic limit. Let me just write that as a coordinate. This is 80 and 5.9, right? On the line in figure 3.1, draw a cross to show the limit of proportionality and label this cross with the letter P. What's limit of proportionality? It is a point until which an object will obey Hooke's law. How do you know an object is obeying Hooke's law? It will have a force extension graph that passes through the origin and has a straight line, and as long as the line remains straight, it is obeying Hooke's law. As soon as the graph starts to move into another shape or obtain another shape, it will have reached its limit of proportionality, and that occurs right over here at this point, which is at 60 millimeters of extension, and the y value for this is so that's 5.8, 5.6, and this is 5.4 Newton. Okay, so the limit of proportionality is reached at 60 millimeter and 5.4 Newton. You don't need to write the coordinates. I'm just making it easier for myself. Okay, we also need to mark it with P, the letter P. Right. On the line figure 3.1, draw a cross to show the elastic limit. Label this cross with the letter E. Elastic limit will be the point until which the object extends under elastic. The point until which the object will extend in an elastic manner, or the point until which when you remove the load it will go back to its original length. And this was already mentioned in the question. The sample behaves elastically up to an extension of 80 millimeter. That means 80 millimeter is the elastic limit. That's over here, right here, and we'll label this with E. Okay, this is supposed to be a cross. C. The sample in B has a cross-sectional area of 0.40 millimeter square. We'll also, of course, for calculation purposes, convert this from millimeter squared to meter squared. And for that, you will need to divide this value of 0.40 by 1,000 squared. And the sample has an initial length of 3.2 meter. For deformations within the limit of proportionality of the sample, determine the spring constant. The spring constant is equal to the force, exerted force or applied force divided by the extension or the gradient of E of a force extension graph until the limit of proportionality. You can find the graph or use any coordinate. Let's see, which one am I going to use? Let me use this coordinate over here of 40 millimeters extension, and this would be 4, 3.8 and 3.6 Newton. So 40 millimeters is 0.04 meter of extension and 3.6 Newton of force, which is equal to 90 Newton per meter. Part 2, the Young modulus of the material from which the sample is made. Determine the Young modulus. Okay, so Young modulus is equal to stress over strain, and that would be equal to force multiplied by length divided by area into extension. Now, as you can notice, or let me write it this way, we already found the spring constant, which is equal to force divided by extension. That means Young modulus would be equal to spring constant multiplied by original length divided by cross-sectional area. So that's equal to 90 multiplied by 3.2 divided by cross-sectional area, which is here you'll need to convert 0.4 millimeters squared to meters squared, and this is equal to 4 times 10 raised to negative 7 meters squared. So that's the cross-sectional area here, and this leads to 7.2 times 10 raised to 8 pascals. Notice how the unit of Young modulus is the same as unit of pressure, and that's because when you find stress over strain, strain has no units because the units of length in the denominator, the units of extension and length cancel out, so you are left with the unit of stress for the unit of Young modulus, which is also Pascal. Part D, determine an estimate of the work done on the sample as it's extended from zero extension to its breaking point, and explain your reasoning. Okay, work done can be found using a force extension graph by finding its the area under this graph. Let me just erase all of the working here so we can have a better workspace, make things more clear. Now if this was the graph, if the shape of this graph was a definite shape, we would have found it much easier, but that's exactly why the question is asking you to estimate. Now up until the point where the graph is a straight line, which is this over here, 60 and what was this, 4.6, or is it, yeah, it's 5.4, right? This, up until this point, the graph has a shape of a triangle, so we can just find the area of triangle, and to that we'll need to add the area of the remaining region. Okay, this point is 192 meters, and when you look at this shape and you need to estimate the area, we can estimate this shape to be a trapezium. An area of trapezium is equal to half multiplied by the sum of parallel sides multiplied by the distance between them. So the distance between them would be this length over here, which will be 192 minus 60, and that's 132, right? That's 132. And then the parallel sides are this length over here, which is, as you can see, 5.4, and this length over here, which would be 6.8. So to find the work done, you will need to add the area of triangle to the area of trapezium, which will be half multiplied by base and height for the triangle, that's 60 multiplied by 5.4, or not 60, that's 60 millimeters. This will need to be half into 0.06 multiplied by 5.4, and to that you will add the area of trapezium, which is half into sum of the parallel sides, which are 5.4 and 6.8 multiplied by the distance between them, which is 132 millimeters, and that's 0.132 meters, and the sum of this is equal to 0.97 joules. You need to do all the working in the right space, so be careful of that. E. A second sample of the same material has a larger cross-sectional area. Now here they're telling you two things about this object. If the sample is of the same material, what that means is the Young modulus value for this sample remains the same. And again, Young modulus is equal to force into length over extension into area, or it is also equal to the spring constant multiplied by original length divided by cross-sectional area. Here the new sample is going to is going to have a larger cross-sectional area. So the cross-sectional area would decrease than the original sample, but the same initial length. Okay, so this here is constant. The two samples are each deformed with the limit of proportionality. That means they are going to obey Hooke's law, and so this formula will apply to them. State and explain qualitatively how the spring constant of the second sample compares with that of the original sample. Okay, let me just make the subject of formula, the spring constant, the subject of formula, so I can explain it better. Now we know that the original length of both samples is the same, and that means the spring constant will be proportional to directly proportional to their Young modulus and the cross-sectional area. Since Young modulus also remains constant, that means spring constant will vary when the cross-sectional area varies. And because the second sample has a larger cross-sectional area, that means it will also have a larger spring constant. And a larger spring constant means for the same extension, you will need to apply a much larger force, or it will be harder to extend the new sample by the same amount of extension. Question 4. A progressive transverse wave travels from left to right. Traveling from left to right is shown at an instant in time in figure 4.1. R and T are points on the wave. State the phase difference between the points R and T. Okay, so the distance between R and T is equal to 3/4 of a wavelength, because, okay, so if we were to look at this diagram, here is the entire wavelength, and let's say this point is the first quarter, and then this one is the second quarter, and so on. So here's the third, and here's the last quarter. And so if you follow the same pattern, here is the first quarter, here's the second, third, and then fourth. And the distance between R and T is equal to 3/4 of a wavelength. And to find this distance in terms of angles, you would need to multiply that by 360 degrees. If they had asked you in terms of radians, you would have said 3/4 multiplied by 2 pi, but this is degrees, so we'll go with this answer of 270 degrees. On figure 4.1, draw an arrow at point T to show the direction of movement at T at the instant shown. Okay, so the wave is traveling from the left to the right. What that means is all the particles from the crest to the trough will point upwards. That means from the crest to the trough, all the particles on the wave will point upward, and from the trough to the crest, all the points will have direction of movement vertically downwards. So point T is between the trough and crest. That means all of the points between these two regions will be pointing downwards. So T will also have an arrow pointing downwards. Part C, the horizontal distance between R and T is 0.62 centimeter. Let's just convert it to meters right away. It will be 0.062 meters. And we can see, we already know this is equal to 3/4 of a wavelength. So the wavelength would be equal to 0.062 multiplied by 4/3. The speed of the wave is 0.27 meter per second. Calculate the frequency of the wave. So wave speed is equal to frequency multiplied by wavelength. And so the frequency is wave speed divided by the wavelength. Which means frequency is equal to 0.27 divided by 0.062 multiplied by 4/3. And this is equal to 33 hertz corrected to two significant figures. D. The wave is a water wave produced by a dipper S1 attached to a vibrator and in a ripple tank. An identical dipper is attached to the same vibrator. The two dippers produce an interference pattern on the wave in the tank. What's interference? Interference occurs when two waves overlap, leading to constructive interference or destructive interference. The wave crests from each source are represented by solid lines on figure 4.3, and the crests and the wave troughs are represented by dashed lines. At point P, you can see the crest of wave from S1 overlap with trough of another wave. At point P, the wave from S1 has the same amplitude A as the wave from S2. Describe and explain the amplitude of the resultant wave at point P. Okay, let's start with constructive and destructive interference. Constructive interference occurs when waves overlap in phase or when the crests and troughs of two waves line up. Let's say you have this wave from S1 and this overlaps with this wave from S2. When they overlap, let me just mark this one in green. When they overlap, the amplitudes or the energies will add up because they are in phase. So you have the green wave lining up with the blue wave, and during interference the energies or the intensity or the amplitudes add up. So this will result in having the amplitude multiplied by 2 or getting doubled. If you had A here, for each wave you will have 2 times of that amplitude or the energy. On the other hand, if when destructive interference occurs and you'll have 2 waves overlapping out of phase, or the crest of one wave will line up with the trough of the other wave. So you'll have wave from one source being out of phase with the other wave. Now as you can see, if this was wave from S1 and this was wave from S2, the amplitudes will have negative sign. If we denote first one with positive and second one with negative, since the amplitudes are equal in magnitude, they would cancel out. If this is plus A and this is negative A, the sum of the amplitudes in interference would be A minus A, which is 0. And so this is destructive interference, where all of the amplitude or all of the energy gets cancelled out. This is interference out of phase, and that's exactly what's happening at point T, which we can see when the crest of first wave lines up with the trough of another wave, which we just saw will lead to destructive interference. Question 5a, state Kirchhoff's second law. According to Kirchhoff's second law, the algebraic sum of potential differences and EMFs across a closed loop is 0. Part 2 asks you to state the conservation law that gives rise to Kirchhoff's second law, and this results from the law of conservation of energy. B. A circuit contains a cell of internal resistance and 2 resistors of resistances R1 and 2 as shown in figure 5.1. Let's take some time to understand internal resistance here. Whenever you have internal resistance in a circuit, the EMF, which is the total energy supplied from the power source, will be distributed between the lost volts and terminal potential difference. What does that mean? Lost volt is the potential difference that's supplied to the internal resistor. So lost volts is equal to IR, and terminal potential difference is the potential difference that's supplied or that's accessible to the circuit, the electrical components inside the circuit. So that's often denoted by capital R. So if you were to measure the potential difference across the internal resistors, you would find the value of lost volts, whereas using this voltmeter, which measures the potential difference for the electrical components inside the circuit, this voltmeter will give you the reading of terminal potential difference. This is all the potential difference from the EMF that's supplied to the circuit or all the electrical components inside the circuit. The remaining energy or the remaining voltage is supplied to the internal resistor. So just keep that in mind. The total energy from the energy source or the power source is distributed between internal resistor, which is known as lost volts, as well as the terminal potential difference, which is supplied to all the electrical components of the circuit. The potential difference across the two resistors is V. Now R1 and R2 are connected in parallel. That means the potential difference across both of these resistors must be the same. They'll have the same value of potential difference. The current in the cell is capital I. So the current in all the components in a series circuit is the same. That means the current that's passing through the internal resistor is also I, capital I, and the current inside the circuit, the remaining circuit, is also I. Now the value of current will be different for when you consider the resistors, and that's because according to Kirchhoff's first law, the sum of the currents moving into a junction will be equal to the sum of the currents moving out of it. When current moves from the power source up until this junction, it will have a value of I, and then it will get divided into, let's say, I1 and I2, which will flow through R1 and R2. And once again, when the currents flow out of the resistors and meet at this junction, they will sum up to the same value of current which was driven out of the power source, which also moves through the internal resistor. That's according to Kirchhoff's first law. Now that we have an understanding of the circuit here, we can move forward using Kirchhoff's laws to show that the total resistance of the external circuit is given by this formula here. Alright, according to Kirchhoff's first law, the total current is divided between R1 and R2. Therefore, the total current is equal to current in the first resistor plus the current in the second resistor. And then we have Ohm's law, which states that V is equal to IR. Therefore, current is equal to the potential difference divided by the resistor. And following this, we know from the information given in the question that the potential difference across the two resistors is V. Both of them have the same value of potential difference, and that's because they are connected in parallel. And as there is no other electrical component in this circuit, that means the terminal potential difference is also equal to V. Remember, terminal potential difference is all of the potential difference or the voltage applied to electrical components of the circuit. So when you want to derive the total resistance using Kirchhoff's first law, that means total current is equal to current in the first resistor plus current in the second resistor, and you substitute Ohm's law into the value of resistors, that means the V by R total is equal to V by R1 plus V by R2. So here we are talking about the current in the resistors using Kirchhoff's first law, and in place of the current we'll substitute their values of potential difference and resistance. The reason I have used V for all of the resistors is because R1 and R2 are connected in parallel, so they'll have the same value of potential difference, And because there is no other electrical component in the circuit, that means the value of terminal potential difference or the total potential difference applied to the circuit is also going to be V. So you following this, you can divide both sides of the formula, both sides of the equation by V, which leads you to concluding that inverse of total resistance is equal to the sum of inverse of R1 and R2. Part 2, the electromotive force of the cell is 1.5 volt. So again, EMF is equal to I into internal resistance plus I into R, keeping in mind that the current through both of the components will be the same, so you can take that common, multiply by the sum of the resistance values. When the values of R1 and R2 are 10 ohms and 15 ohms respectively, the potential difference measured by the voltmeter is 1.3 volt. Okay, so we have R1 and R2 connected in parallel, and the voltage across them is measured as 1.38 volt. R1 is 10 ohms and R2 is 15 ohms. They are connected to a cell of 1.5 volt, and the value of internal resistance is unknown. Calculate the internal resistance of the cell. So I'll continue using this formula where EMF is equal to the common current multiplied by sum of resistance of the circuit plus internal resistance. We're supposed to find this value over here. That means you will need to know the total resistance of the resistors in parallel as well as the EMF value as well as the current in the circuit. What is the current in the circuit? It is the total current, which means I is equal to V by R. To find this total current, you can consider the circuit where the potential difference is the terminal potential difference, and that's 1.38 volt divided by the total resistance of parallel resistors, and this will be 15 into 10 divided by 15 plus 10, or you could just use the formula from the previous part. Both of them will lead to the same answer of 6 ohms. So 6 ohm is the resistance of the circuit excluding the internal resistor, and this will lead to a current of 0.23 ampere. Now we know the current. We also know the resistance of the resistors in parallel as well as the EMF. We just need to find the internal resistance. So that's 1.5 is equal to I into R, capital R, which is 6 ohms, plus 0.23 multiplied by internal resistance. And when you rearrange the equation, you'll find that internal resistance is equal to 0.52 ohms. See, a third resistor is added in parallel with R1 and R2. Now, first thing here you need to know is whenever you connect more resistors in parallel, the total resistance in parallel will decrease. Following this, state and explain the effect, if any, of this change on the current in the cell. So, current is inversely proportional to resistance according to Ohm's law, because V is IR, and when you substitute, you'll find this relation. When you rearrange, you'll find this relation. So, if the total resistance will decrease because when you add more resistors in parallel, the total resistance will decrease, the current in the circuit will increase. And following this, you are supposed to state and explain the effect of adding a third resistor in parallel on the potential difference measured by the voltmeter. So the voltmeter measures the potential difference values of these 3 resistors now, right? So we know again, according to Ohm's law, V is equal to IR, where V is proportional to R. If the total resistance in parallel decreases, that means the potential difference across the resistors will also decrease. And as we know from the parts discussed earlier, the EMF is equal to lost volts plus terminal potential difference, where terminal potential difference is the voltage applied to the resistors. If the voltage applied to the resistors decreases and the EMF remains the same, because we are using the same power source, that means the value of lost volts will increase, or the potential difference across the internal resistor will be greater. And therefore, the potential difference measured by the voltmeter, which is the terminal potential difference, will be smaller now. Question 6. Nuclei of an isotope of samarium each contain 62 protons and 85 neutrons. State the nuclide notation in terms of the atomic number and the mass or nucleon number for this isotope. Atomic number is the number of protons, which is also equal to the number of electrons in a neutral atom, whereas the mass number is the sum of protons plus neutrons. So this is a samarium atom with 62 protons and 147 nucleons in its nucleus. B. This isotope of samarium is radioactive and decays by emitting particles. Gamma radiation is not emitted. So that leaves us with beta and alpha radiation. The energy spectrum of the emitted particles is shown in figure 6.1. While learning about radiation, you'll learn that the energy of alpha particles is always discrete, meaning you'll only see a single line in this graph for alpha radiation, whereas for beta radiation you will see a curve or a continuous range of energies. So this is going to be alpha radiation, and the question asks you to explain exactly that. Explain how the isotope emits alpha particle and not beta particles as shown by the diagram. The isotope of samarium decays to an isotope of neodymium. Give the radioactive decay equation for this decay. Okay, so we have samarium with 62 protons, 147 nucleons, and it decays by alpha radiation, as we just said earlier. By an alpha radiation is a helium nucleus, so it will cause loss of 2 protons and 2 neutrons, or it will reduce the atomic number by 2. It will reduce the mass number by 4. So that leaves you with the new nucleus having 60 protons and a mass number of 143, as well as the helium nucleus. C. A baryon is composed of 3 quarks, which all have different flavors. Quarks are fundamental particles, meaning they cannot be broken down into further particles. The baryon has a charge of 0, so these quarks have charges. 2 of the quarks in the baryon are an up and a bottom quark. An up quark has a charge of plus 2/3, whereas a bottom quark has a charge of negative third. Determine in terms of the elementary change the charge on the third quark in the baryon. So we know there are going to be 3 quarks and the total charge is equal to 0. One of them is an up quark, the other one is a down quark, and when you add the last quark, which is unknown, it should be equal to 0. So therefore x is equal to 1/3 minus 2/3 of a charge, and that leads you to negative 1/3 of a charge. State a possible flavor for the third quark in the baryon. Okay, so negative charges are carried by down, strange, or bottom quark. We just know now, we know that this is not a bottom quark, otherwise the question would have said so. The question says two the quarks in the baryon are, one of the quarks in the baryon is a bottom quark. That means the other negative quark must be another negative quark. That leaves you with a down or a strange quark. And this is it. We are done with this paper. Thank you for watching.